This is figure 3 in chapter 36. It shows just what we've been talking about, a single slit with a light passing through the slit and then projecting a interference pattern on a distant screen where you see this bright central maximum and then dark adjacent to that. Then it gets bright again, dark, bright, dark. We can get the pattern from, you can think of the slit opening as a source of very many wavelets spreading out from all the points in the opening of the slit. Add up all the wave functions for some given angle theta, and then intensity we got from the square of the wave function. You could do a similar thing for a circular opening. Then we call it an aperture instead of a slit. So a circular aperture of diameter d. So this figure 25 in this same chapter shows like a screen that's opaque except for a small circular aperture of diameter d. And then what you get, it's kind of interesting, you get an interference pattern that is rings. So it's bright central maximum and then surrounded by a ring of destructive interference, and then another bright, and then another ring of destructive interference, and so on. So instead of bright central line from a slit, you get a bright central circle surrounded by a minimum. This is important because lots of times what we're doing is looking at light through circular apertures. For example, the iris of our eye, microscope, the telescope. So this is something that we have to contend with all the time, diffraction with circular apertures. And it's an interesting phenomena, but can be a problem in terms of trying to see things with microscopes and telescopes, and so forth. So I want to talk about that a little bit. And I'm going to focus mostly on astronomy and telescopes, but the similar things apply to all kinds of different optical devices. In this case, with the slits, it took some effort to get the interference pattern, the intensity as a function of angle. But then we were able to find that the minimum, actually we were able to find it before that, but either way you can see that the minima in the diffraction pattern occur when a sine theta equals lambda. The first minimum is a sine theta equals lambda, so I'm calling it theta 1. So a sine theta 1 equals 1 lambda. Tells us at what angle theta 1 the first minimum will occur if the slit width is a and the wavelength is lambda. You can play a similar game with the circular aperture. It just turns out the math turns out to be much more difficult, literally beyond our level. So if you do it though, I think I remember doing it maybe as a grad student or something. It's a complicated problem, but you can derive a function that represents this pattern of circular rings, and you can solve for where the first minimum occurs, and you get this result, just stated without proof, that the angle out from the center of the pattern to the first minimum, theta 1, obeys d sine theta equals 1.22 lambda. Not exactly 1.22, that's rounded off a little bit, but that's good enough. D is the diameter of the opening, so that kind of plays a similar role to A as the slit width. D sine theta 1 is approximately 1.22 lambda. So I'm just stating without proof. It comes from solving this problem, adding up all the wave functions from all the openings in the circular aperture. But it's useful enough, this equation, that it's worth pulling it out of thin air and talking about it. So why is this useful? Let me go on to the next slide here. So this is a picture from the book, which is figure 27. It shows a bunch of light sources viewed and photographed through different size apertures. So there's 3 different pictures. The bottom picture shows these 4 different light sources through a large aperture. like maybe through a large, camera lens or something, and or if it's a telescope, maybe through a large diameter telescope. And then here, the middle picture shows the same four objects, but through a medium-sized aperture, maybe like a smaller telescope. And then the top image shows same exact scene for light sources, but through a small telescope or a small aperture. And what you see is in the bottom image, you see these four different circles of light representing four different light sources. Maybe think of them like they're stars. The second picture with this reduced, we call it medium-sized aperture, you can see a diffraction pattern from each one. So around each light source are rings, bright and dark rings. And in the top image with the very small aperture, it's the same, except the diffraction pattern is more spread out. There's a larger angle out to the first minimum of the diffraction pattern of each light source. And what happens is these two here, they're numbered 1, 2, 3, 4, these light sources. There's two of them that are closer than the others. And you can see numbers 3 and 4. When you reduce the aperture size, their diffraction patterns, because they keep spreading out as you reduce the aperture size, eventually start to overlap. And in this top image, they blur together, and it's very difficult to even see that there are two separate images. So we say the resolution is much worse when we use that small aperture. We can't resolve very well that there are two separate light sources there. So the size of the opening relative to the wavelength determines our ability, restricts our ability to resolve fine detail. And this is true regardless of, you may have an absolutely perfect telescope, nothing wrong with it, but just the nature of light as a wave will start to prevent you from resolving fine detail at some level. So look at this this diagram over here. It shows a circular aperture in an otherwise opaque screen and a light source like a distant star. And then on a projection screen, you can see a diffraction pattern from that light source, which is spread out a bit, right? That's what diffraction does. So that central peak there is essentially an image of the star through that aperture, but it has broadened a certain amount due to diffraction. The first minimum of the diffraction pattern occurs at an angle indicated here, away from the center line, theta 1, given by that equation I threw out. Sine theta 1 equals 1.22 lambda over d. So we say if there was another light source nearby, then if it was too close, we'd have trouble resolving it. And if it's farther away, we could perhaps resolve it. And sort of the cutoff, this is just a rule of thumb, but as a cutoff would be if there was another light source that sent in light along this same line through the aperture to the first minimum, so I'll draw one in here, then its diffraction pattern would spread there. So its maximum would be at the minimum of its neighbor's diffraction pattern. And we say, just as a rule of thumb, that's about as close as you're going to be able to resolve. If that was any closer, these diffraction patterns would overlap too much and we would not be able to tell that there's two light sources. And if the star was farther away in angle, their diffraction patterns would suitably avoid each other's overlap and would be able to see that there's two separate objects. So that rule of thumb, using the first angle, the angle of the first diffraction minimum, as the resolution cutoff, it's called the Rayleigh criterion. So let's see. Here's an example. And maybe you're wondering about this calculation down at the bottom of the screen. So that's what this is coming to. This is, in this picture, I have the pictures of Pluto. So on the right, this is Pluto in images taken in 2015 from the New Horizons space probe, which was sent to Pluto. It did a flyby and took all kinds of cool images. And so now we know a lot about what Pluto looks like. It's got this very bright region of ice, got some darker regions. Very interesting place. Before 2015, the image at the left, that was our best image of Pluto. And this was using the Hubble Space Telescope. The Hubble Space Telescope has a 1.4 meter diameter. And so that limits the possible resolution, even if the optics are designed perfectly. So let's calculate what the angle is. So for the Hubble, so I'm looking at this 1.22 lambda over d. So there's lambda, I just grabbed a visible wavelength, 6 times 10 to the minus 7 meters. That's sort of red or something. And then diameter, 1.4 meters. And then there's the 1.22. So the inverse sine of that is 0.00003 degrees. So that means if two objects are any closer in angle than that, then Hubble won't be able to resolve them. Here I've converted the angle because really small angles, sometimes astronomers use other units, and there's a unit called an arc minute. Have you heard of that? There's 60 arc minutes is 1 degree. And then even smaller arc seconds. So 60 arc seconds is 1 arc minute. So converting that degree into arc seconds comes out about 0.1 arc seconds. So that is the diffraction limited resolution of the Hubble Space Telescope. That means that's the laws of nature don't let it do any better than that, no matter how carefully the surfaces are designed and built. So astronomers are always will do a couple things. They're trying to see things that aren't very bright, and then for that it's useful to have bigger telescopes because you collect more light. But they're also trying to improve resolution, get more detail. And sometimes the more bright part's not so important, just the resolution part's important. So you can do a trick. So this is, you see this picture is it's a set of telescopes. There are 27 of them in an array. It's an array of telescopes that can be spread out over a very large area. So naturally it's called the Very Large Array, VLA. That's really its name. So each of these telescopes is a radio telescope 25 meters across. And they can be moved around on tracks to have different configurations. You can move them to a maximum distance apart of 36 kilometers altogether from end to end. And then as far as resolution is concerned, they collectively can act like a 36 kilometer telescope with d equals 36 kilometers. And they don't collect as much light as the 36 kilometer telescope, but so they don't see the super dim things, but the resolution is excellent. They use a wavelength of about 7 millimeters. I'm sorry, not visible light, right? 7 millimeters. And so if you calculate with 36 kilometers, that's about a resolution of 0.05 arc seconds, so even better than the Hubble Space Telescope for these wavelengths. Last thing I want to mention is the highest resolution astronomical image was just recently recorded a couple years ago, 2017. This is an image of a black hole event horizon, and it used an array of telescopes across the whole planet. So that's really maximizing. And the resolution is about 0.00002 arc seconds.